I want to talk about measuring impedance of different components using a spectrum analyzer with the tracking generator. And first of all, I want to say, why is this important? Why can't we just use components as they are and be happy? And it's because we always get surprised about how components perform. And this is why we have all sorts of EMC problems, because we use components differently. And so they just perform a little bit different from what is expected. For example, here is a switch mode power supply with some really big capacitors, and this was of course supposed to perform really good, but when it was implemented with the way that stuff was connected together with long thin wires, everything became resonant, and we had a huge EMC problem from this switch mode power supply. So if we had tested the way that these components they interact, not just the component itself, but the way that they interact with each other, we some wires, we would have seen that we had a really big resonant problem at the harmonics of this converter. So how do we measure the impedance of a capacitor, for example, without affecting the capacitor and creating a new resonance? So here is what people normally do. They normally just zero the analyzer with a through connection like this, so that the input and output is connected together, and then they put in their tester. This it could have been other connectors like the through connectors, and then here is a little 100 nanofarad capacitor. And what we have here is a lot of reflections, because this capacitor goes into a resonant circuit with the cables to the analyzer. And here is a curve of that phenomenon. Here we'll show the curve, so you can see all the ripple, and I will show the curve at different frequencies. And this way you can see that there is a lot of ripple on the measured signal. It is of course to see what is going on, and the self-resonant frequency is almost correct. It is a little bit affected by the cables. So if we compare this method of having an attenuator in each side, at the moment I'm running with 5 dB in each side. This means that the test object will be tested at a resistive impedance that is not affected by cable resonance or length of the cables, so that the curve will get a lot less ripple and will not affect the tested object by the cables or the analyzer. So what I have here is a 0 ohm resistor in the middle, and then my two 5 dB attenuators, and I use this one as a reference. So I zero the analyzer for each frequency range that I want to measure, and then I put in my test object. Here it's also a 0 ohm resistor, and in this case 100 nanofarad capacitor. So at the moment I'm doing a full span. So this is the full span with 100 nanofarad, and as you see, there's a lot less ripple. It is about 0.5 dB of ripple, and if you want this ripple to be even less, then you could of course make these attenuators each side a lot higher, but this will of course affect our dynamic range. How many dB can we measure? Because this will eat 5 dB of the power, and this will eat 5 dB of the sensitivity. 10 dB is very smart because it's easy to see when we go into the tracking generator menu, and we will see that we have a flat 10 dB loss from 0 to whatever the analyzer can do. This just proves that this device is flat in response, and it has the right impedance and is working. And before I did all my tests of all my different test setups, I tested all of them with 0 ohm resistor and zoomed in greatly so that I knew that the curve was exactly the same as my reference unit. I'm also using exactly the same resistors from my resistor kit, so that I know that they all perform exactly the same. And then we can have a look at, for example, a 100 nanofarad capacitor. And if we zoom into the results, we will see that the resonant frequency is here, and then we will see that the left portion of the signal is the capacitor side, and the right side of the resonant is the inductive side of the component. If we try and change the way that we test 100 nanofarad capacitors, for example, let's take and connect the capacitor like this. I don't know if it's easy to see on this video, but what I've done here is I have made this the track so it goes through the capacitor. This is how you would normally use a capacitor if it is a critical performance position of your schematic. You would of course take the wire through the capacitor, in and out of each side of the pad of the component. And if we compare this number 7 with number 6, so the first curve here is the 100 nanofarad made like this. If we note, I changed the span so it is 100 megahertz. Let's see how deep it goes. 63 dB, and the resonance frequency is 16.4 megahertz. So let's compare this number 7. So the resonant frequency is a little bit higher, 7.4, and the dB, the attenuation, is about the same. So this is number 8. Here we got 3 100 nanofarad capacitors side by side. I haven't done anything fantastic about the way that they are connected. So this is the purple line. It is quite a lot lower. There is an odd resonance at the lower frequency. I will store this in the memory and compare with the next one as well. And this one is a lot more interesting. I got 3 times 100 nanofarad. I cut some slots so that the signal must go through the capacitors. Let's have a look at the curves. Now it's the blue one we're seeing, and the other two, that is the two previous tests. And what we see now is a lot lower signal and a lot wider frequency range, and there's an even more powerful resonance. Let's try and compare a 100 nano and a 10 nano and see the two different curves. Here the yellow is the 100 nano, and the purple is the 10 nano. Let's try and combine different capacitors. In this case, I actually took 3 of them. 1 nano, 10 nano, 100 nano. And here we have the blue curve, the combined result of all 3 of them. And I left the other curves here as well. So the orange, no, this is the yellow is the 100 nano, and the purple is the 10 nano. And here is the combination. So something actually happens here in this area in between these two capacitors. So that was a little bit about capacitors and how they behave. To get this dB reading into impedance, I performed this calculation, or this is like a translate sheet, where I can translate the attenuation factor measured in dB that we measure on this setup. Of course, if you the lower the resistance or impedance you have to ground, the less signal you're gonna get, right? So the dB attenuation can be translated into an impedance in ohms. I only bothered to do the calculation down to 48 because anything under 100 milliohms is not really that big a deal for the switch mode converters that I'm working with at the moment. But you could actually handle up to 70 dB of dynamic range with the cheap analyzers like this. Quite a lot more dBs if you have one that is a little bit more expensive. So it's all about the dynamic range and how far you want to take the calculation sheet. Obviously, if you want to measure inductors, you want to put the inductor in series with the signal and not to ground, right? So that is when you remove the 0 ohm resistor here in the middle and put in your inductor of any type you want to measure. And this could be also a filter, not just an inductor like this, but a combination of an inductor and a capacitor. And this is where the real fun begins. Then you get a really, really good attenuation at a really, really wide frequency range. I have tested all sorts of inductors and filter components that we're going to use in some switch mode converter designs. The most commonly used in Prevas projects, that will be the lossy ferrites from Murata. This one is the 1000 ohms at 100 megahertz, and here is the type. So let's try and say at the dB sheet. So 1000 ohms should be a little bit more than 20 dB, right? So let's have a look at the curve for this test number 2. And I measure 19 point something. So that means it is a little bit from that value, and I just hit the peak button, and I see the best frequency is 220 megahertz with the highest attenuation, and it is it is about 800 or 850 ohms, right? And from this point on, the frequency gets up and the attenuation gets lower and lower again. So this is actually the self-resonance point of this part, and this is what you should not be tricked at. The nice numbers that they give in the data sheets. Normally you would think that, oh, we have this and this attenuation at this and this frequency, and the higher the frequency gets, the more attenuation you get. Most likely this is not what you're gonna get. It will be the best value and the best figure. This is what they're trying to sell you, right? If you combine this part with capacitors, then you will see something fantastic happening. So this is my tester number 3. Again, the water part, the 1K at 100 megahertz, but here it's in combination with a 100 nanofarad capacitor. Now let's look at the curve. Look at this attenuation, and this is all the way to 500 megahertz. And the self-resonance is 17 megahertz. This is of course the capacitor that we're talking about. We could have used, in this case, we could have used a capacitor with lower value, so we will have a better dip in the higher frequencies. Let's try and do that. And this is tester number 4, the Murata 1K device and only 1 nanofarad. And in this case, we get a peak at 166 megahertz at minus 61 dB attenuation. And look how wide the attenuation is. The resonant here is not really super narrow and super deep, and this is because the behavior of this lossy ferrite is a low Q loss. So it's not able to create resonances of high Q together with the capacitors, and this is a huge advantage in filters. Let's try and combine some more capacitors here. So this is the 1 nanofarad, but now I put on a 100 nanofarad as well. And again we have this Murata 1K device. Let's have a look at the curve. Now see how low attenuation we have at a really wide area. All the way from, let's look at the marker, 200 megahertz and all the way down to 10 megahertz. And we have 60 dB of attenuation. This is like 10 milliohms of impedance to ground. So this is super effective way to kill noise and ripple and whatnot. Yeah, so this is what I wanted to show about how to measure the different components and how you can make stuff perform a lot better. Oh, as a little bonus, there is another one for you guys. Let's look at this one. Test number 5. 2 of the 1K Murata devices and some capacitors connected to ground in a very special and very smart way. See, the idea here is that the inductance in the capacitors, the current into the capacitors actually goes like this way to ground, right? So if this goes this way and the other one goes that way, you see what happens with the magnets in these two parts? They go each a different way. So they zero out the impedance, the inductance inside these capacitors becomes almost zero. And this is a really, really good way to optimize your capacitors. Don't put them side by side, but put them like this, up and down, to a new set of ground VS in each side. This is also a super effective way to minimize your ground impedance to your capacitors. Enough talk. Let's see how this performs. So, I have reached the dynamic range of my analyzer in the setup and the calibration that I have done here. Also, you will see that I have this is exactly the same signal as no signal, and this is flat all the way up. I think we should maybe create a new calibration and do a full sweep. And also you will see that the capacitors that I used are a very, very low value. So that means I have almost no attenuation at very low frequencies. But this could be an experiment for some data lines going in and out of something critical. And I needed, a nice and clean high frequency in an output for a receiver or something, but I still need quite high speed data going in and out of this area. So as you see here, if we go down in frequency, I have no attenuation at all at 20 kilohertz. I could easily do some megahertz of communication, and at the frequencies where the radio would work at 400 or 500, we will have a huge attenuation and will not have any noise going in and out of this area. But let's try and zoom out and do a more full span of this. Let's try and be fair and compare number 2 with a full span curve. So this is all the way up to 3.2 gigahertz. And we will see that up in the very high frequencies up here, we have almost no attenuation at all. And to be fair, we need to see the full sweep also at test object number 3. Again, the Murata lossy filter with 100 nanofarad. And as we see here on the curve, there's a huge dip at 21 megahertz, and this is half of the way to 3.2, right? So this is 3.2 gigahertz, and again almost no attenuation between 2 and 3 gigahertz. So that means the capacitor is absolutely useless and the inductor is absolutely useless at these high frequencies. Let's look at the previous one again. This is 1 nano and 100 nanofarad in parallel, and see how they perform at 3.2 gigahertz. And again, up in the very high area between 2 and 3 gigahertz, almost no attenuation. And because we're using 2 different capacitor values, we have this funny resonance at the low frequency range, as we already talked about before. Now we're just zooming out and looking at a much broader frequency range. So now this is the last curve. This is number 5 again, with the very low capacitor values. And let's see if we are able to do anything good at the really, really high frequencies. And if we look at this curve now, we actually got quite a lot of attenuation all the way up here. So if you want to have attenuation at the very high frequencies, of course what we should have done here is used another device, maybe also from Murata, but specified to have attenuation at a much higher frequency. So it's not that easy to make attenuation at the really high frequencies. Alright, thank you for watching. Good night. Bye.